Okay, after a couple of, I thought they were difficult modules, I think today is a much more straightforward one. Exponential functions. Okay, so we've seen that exponential functions give a good model for unconstrained growth. So there's a differential equation y prime equals ky, where k is a positive constant, and to get to k we just let k be negative. So we can solve a differential equation pretty easily. So given y prime equals ky, and so k, if we figure out what kb is for this k, you know, which base gives this number as its derivative at 0, we then know that the solution is y equals any number whatsoever c times b to the t. The base is b. Okay. If we didn't like b as a base, say we wanted 2 as a base, we could get y equals, or we could replace b to the t by 2 to the power kb divided by 6.93 times t, right? Because by the chain rule, we're going to multiply by kb divided by 6.93 because of that part of the chain. And then because our 2 is our base, we're going to multiply by 0.693. So the 0.693 is cancelled. Or we could use base 10. And there we've got to divide by 2.3025 because K10 is 2.3025. So we divide and multiply by the same number. So it ends up we just keep on multiplying by KB. And so we can do that for any base capital B. So we get a constant times that base capital B to the power AT, where A is just the k of the little b, which is the k we're given, divided by the k of the base that we want. This is too complicated. We want things to be 1, because then we don't have to worry about the formula for it. So we want the base capital B to have that property that its derivative at 0 is 1. There is such a base, and classically it's been called the number e. So that's what we're going to call e. It's very simple, right? Because given the problem y prime equals ky, y0 equals c, then the solution is just y equals c times e to the kt. Okay, because when t is 0, y is going to be c. When we take the derivative by the chain rule, we just have to multiply. We're just going to multiply by k. So this means the derivative of e to the kt is k times e to the kt. And in particular, the derivative of e to the t is e to the t. Okay. In the video that follows this one, as I said, I just use an Excel file, a pop to find the number e. And it's the number 2.718 that you might know. It's on your calculator. You might see e to the x. That's the e. So you put e to the 1, you'll get the number e. Okay, exponential decay. Okay, so when b, the base is between 0 and 1, we get exponential decay. Just by looking at the graph, since the curve is decreasing, we know the derivative must be negative. So for example, there's a half x compared to 2 to the x. And we see that they kind of mirror images of each other. So since 1 divided by b to the power x is the same thing as b to the minus x, then that's going to have derivative minus k times b to the minus x. So for example, you might remember that the constant for a half is minus 0.693. And in general, the constant for 1 over b is just negative the constant for b. So let's just do some straightforward examples, like the derivative of 7 times e to the 3x. Okay, we keep the 7 because it's a multiplicative constant. We multiply by that 3 because it's e to the 3x. So that gets us 21, and it's an exponential, so the exponential stays, e to the 3x. And so in general, if you've got c times e to the kx, the derivative of that will be kc, right, because the k comes down, times e to the kx. It's an exponential, so the exponential stays. And we can do much more complicated things now, like e to the x squared. Okay, so that's just going to be a chain rule, right? So we let u equals x squared, and then we've got e to the u. So the derivative of x squared is 2x, so that's why the 2x is there. And we've got an exponential, the exponential stays. So the derivative of e to the x squared is 2x times e to the x squared. Okay, so that's one question I can ask you. I can ask you about formulas. Here's one that we looked at really much earlier when we looked at exponential growth. This problem of Poland and Afghanistan, 2 countries with 2 different populations and 2 different growth rates. And if you remember, the problem was p prime equals 0.01 p, and the initial population was 38 million, so p is in millions here. I think this is back in 1985. And for Afghanistan, we had a prime equals 0.026a. Oh, I forgot the a there, sorry. And a0 is 15 million. So we can just write down the solution to these problems. So p is 38 times e to the 0.01t, and a is 15 times e to the 0.026t. And since we have formulas, we can just answer any question we might be given. So back in the day when we started this course, we used an Excel file to figure out what was the population in 20 years. So for P, for Poland, just plug in T equals 20, you get 38 times E to the 0.2, and that's around 46.41. So that's 46,410,000. And for Afghanistan, it's 15 times E to the 0.52. And that turns out to be 25.23 million, or 25,230,000. Okay, so that's the nice thing about formulas, is just plug and you get your answer. Here's a little bit more of a word problem. Intensity of radiation. As gamma rays travel through an object, their intensity I decreases with the distance x that they have traveled. The rate of absorption, di dx, equals ki. Now, some materials such as lead are better shields than others, such as air. How would we express this difference in a differential equation? Assuming that the unshielded intensity is I naught, write a formula for I in terms of x. Okay, well, the differential equation, right, is I prime equals KL. Now, where the different materials come in is in the K, the rate of absorption constant. Since lead is a better shield, K for lead must be much bigger than the K for air. Okay, so solving this equation, we have I equals C times e to the kx. Then we can find the constant C, because we're told that when there's no shielding, the intensity is I0. So that means C has, so you plug in x equals 0 and e to the k0 is 1. So I is the I naught, which must be this constant C. Hence the solution is I equals I naught times e to the kx. Okay, so that finishes that section.